Okay, this is problem number 1 from the AP Physics 1 force packet. When you're doing these problems, the first thing you're going to want to do is draw a force diagram for every single object in the system. And we have two objects in the system, box A and box B. So, I'm going to draw box A. It's got a mass of 10 kilograms. And I'm going to draw the forces on it. And it's sitting on a surface. So it's going to have 4 forces on it. My first force will be the force of gravity. Then the rope is what's actually pulling box A to the right, and so we'll label that as the tension force. We've got the normal force coming from the table, which is supporting it, making sure it's not going to go anywhere, up or down. And because there's friction between the table and the box, we're going to have the friction force as well. Once I have the forces, I can find as many of them as I can using the formulas. I have a force of gravity formula is mg, and so the box is 10 kilograms. And gravity we know is negative 10 meters per second squared. And so I'll get a force of gravity of negative 100 newtons. It's sitting on a flat surface, and so we know that these two forces, the vertical forces, are going to be balanced. So this tells me that my normal force is also 100 newtons, because it has to have a net force of 0 in the vertical direction. If it didn't have a net force of 0, if one of these forces were bigger than the other, then the box would be accelerating up or down. And box A is not accelerating up or down, it's accelerating to the right only. And so those forces have to be balanced. The problem tells me up here, and we change the typo to 60 newtons, that the force of tension in the rope is going to be 60 newtons. Anytime you're dealing with a frictionless pulley or a massless pulley, that means that you can ignore the pulley. And the only thing it does is change the direction of the force. And so both of these ropes right here, the one attached to box A and box B, are going to have the same tension, which is 60 newtons. And so I'll go ahead and write 60 newtons worth of tension. And that's all I can do right now because I don't know the coefficient of friction. That's what we're trying to find. And I don't know what the acceleration of this box is yet. I can go ahead and go to box B. And box B is easier because it's the hanging box. And so it's only going to have 2 forces on it. It's going to have the force of gravity and that same rope tension force that was suspending it right here. And so the force of gravity is going to be the same as the force of gravity on box A because they're both 10 kilograms. We've got 100 newtons. And this is going to be the same tension force because of that frictionless pulley. Later on we'll worry about pulleys that have friction and mass, but right now anytime you see a rope that's stretched over a pulley like this, it's going to have the same tension on both sides. And that's it. There's no sideways forces or horizontal forces on box B because the box isn't going that direction. It's got nothing pushing or pulling it in the horizontal direction. So at this point we have both of our forces and we can go ahead and combine them to get the net force. And so the net force on block B is going to be, we're going to adding these two forces together. The normal force, I'm sorry, that's a tension force. Whew, I almost called it a normal force. Tension force and the gravity force added together, the two forces that are pointed in opposite directions are going to give me my net force. And so my net force for block B is going to be my 60 newtons minus my 100 newtons, and so I've got a net force of negative 40 newtons. Once I have the net force for any object, I can always apply Newton's second law. Newton's second law is, in case you forgot, mass times acceleration. And we've got the mass and we've got the net force. And so we can go ahead and use it. We've got the net force of negative 40. We've got the mass of 10 kilograms. And we can go ahead and solve for A. And the acceleration of this box is going to be negative 4 meters per second squared. This negative just means that the box is accelerating down. It's headed in the downward direction, and we've called the downward direction negative, and so that's going to be our acceleration. This is the same magnitude of acceleration that box A is going to have because they're attached with a rope. Anytime two objects are attached with a rope, chain, they're somehow connected, they're going to have the same acceleration. Since over here we've called to the right for box A the positive direction, that means that my acceleration, which is in the positive direction, is going to have to be positive as well. So just because we got a negative acceleration over there, that just showed direction. And that we got the negative because the downward force or the downward direction was what we were calling negative. Over here, the positive direction is to the right, and so when you use this 4 meters per second squared for box A, make sure you make it positive. Remember, on these vectors, positive and negative only mean direction. So you've got to be consistent with your direction, and if you want to call to the right the negative direction, you technically can. But since I already called it positive here, and that's what we're used to doing, I'm going to make sure my acceleration is going to be positive. But it's going to be the same magnitude. It's going to be 4 meters per second squared. And so once I know that, I can go ahead and use Newton's second law for the first box. So I can use net force equals mass times acceleration for the first box. And since the box has the same mass as the box B, we already know what the net force is going to be. It's going to be 40 newtons. And positive 40 because it's pointed to the right, the same direction as the acceleration. The net force and the acceleration always point in the same direction in these problems. So once I've got the net force, then I can go ahead and solve for the friction force. Because remember, when I add these two forces together, the friction and the tension, I should end up with the net force. And so, let's scoot this up. We've got the net force is equal to the 60 Newton tension force plus the force of friction. And my net force was 40 newtons. Let's go ahead and replace this as 40 newtons. I forgot to do that. And so once I subtract 60 from both sides, I figure out the force of friction is going to be negative 20 newtons. And again, it's only negative because we've got the friction force pointed to the left, which we've called the negative for this particular box. Once I've got that, then I'm one step away from getting the coefficient. I just have to use the coefficient formula, which is the force of friction is equal to the coefficient times the normal force. And remember, this is a magnitude formula. It'll give you the absolute value. And so you'll always want to make your force of friction positive when you use this. And I'll just plug everything in. I've got a force of friction with a magnitude of 20 newtons, equals to the coefficient, and the normal force is going to be 100 newtons. And why did I divide? I can go ahead and get the coefficient of friction. So that'll be the answer to number 1. Remember, on all these problems, the process is going to be the same. You're going to draw a force diagram for each one. You're going to figure out what the object is doing in terms of acceleration, and you're going to use the net force. 2 ways to find net force. You can find it with mass times acceleration, or you can find it with adding the forces together.